I'm especially glad that I could present, I could announce this talk in the presence of Hans-Jürgen Borchers. That's because I think you are one of the most important students and co-workers of you. Please.
Okay, thank you very much. It's of course a great pleasure and a privilege for me to speak at this conference on algebraic quantum field theory. Well, yesterday when I came here, the first thing I did was to undertake a nostalgic trip to the center of Göttingen, where I hadn't in fact been for a couple of years now, and looking at all the new cafes and pubs, and also the old ones where I myself and my fellow students used to hang out in the olden days. Was a great pleasure. Likewise, talking here at this conference, or attending this conference rather, is also a nostalgic trip for me, and just as it was wonderful to see all these young people and all these new localities and fancy restaurants, I really look forward and enjoy very much to see all these young people here and hear about new results. And this even much more so because, as many of you know, quantum field theory has not really been my main subject for quite some time now. But this is the area, and this is the town where I was brought up scientifically by Hans-Jürgen Borchers. And I have, of course, very many fond memories from here, and I also like to come back to quantum field theory occasionally. I think my last paper, that was in fact something which Bert is really responsible for that, and we had a very enjoyable collaboration, resulting in a paper with Jens Mund, which appeared 3 years ago. So it's not so long time ago that I have been doing something in this area. Anyway, what I want to do now is to talk about the Borchers-Uhlmann algebra and some of its descendants. In fact, fewer, in fact essentially only 2, fewer than I had originally planned. But it turned out, when I started to write down these view graphs, that I had soon filled 28 slides, and I thought this is more than enough, and it's not. So there are a few things that I would have liked to talk about, but has to leave out. So here's just a brief sketch of the topics which I want to mention. First, I want to define the Borchers-Uhlmann algebra, which of course many of you know, and recall the concept of Wightman functionals. Then I will review some well, fairly old results obtained mainly in the 80s and 90s about the abundance of states which satisfy at least parts of the Wightman axioms. A natural question which came out of that was the question, although it may not be of great physical significance, but since, as you know, of course, Wightman fields in 4 dimensions are not so abundant, I think it's nevertheless still a very interesting question, is about whether there exist Bose fields where the field operators are bounded operators. And this is a question which resulted actually from these investigations, and which was taken up, among others, by my good friend Klaus Baumann, who passed away about 10 years ago prematurely, and also by Henning Rehren and co-workers. So this is one thing I want to mention briefly. Then I will come back to joint work with Hans Borchers, which I have put here under the heading non-commutative moment problems. And what I want to mention there also is our work on the connection between Wightman quantum field theory and algebraic quantum field theory defined by local von Neumann algebras. Now I will say a few words about deformed Borchers-Uhlmann algebras. Here I'm just on 2 view graphs or so. I am just making some propaganda for work of Harald Grosse and Gandalf Lechner, where they use this formalism again in a deformed form. And finally, I will say a few remarks about a certain extension problem for states, which was in fact one of the first problems or the first questions about this in this area that Borchers posed to me, and which is still completely unsolved. And I still think it will not be really, it's not feasible to have a complete solution to it, but nevertheless I have recently been convinced that it's maybe worth looking at it again in view of some developments in many-body, non-relativistic many-body quantum physics. Anyway, that's what I want to do at the last. So now let me just start by mentioning the seminal papers in this area, starting of course with Wightman's paper of 1956, where he defines the Wightman functions and proves the reconstruction theorem, namely that the Wightman functions, if they satisfy some conditions, which are necessary and sufficient conditions for the Wightman axioms to be fulfilled, then you can reconstruct your quantum field from the Wightman functions. Now, next come 2 papers. Well, by the way, this paper, I checked it, the word algebra does not occur in this paper. Now, here are these 2 very first papers, which in fact are completely independent. They were submitted in an interval of about 4 weeks. In fact, the paper of Uhlmann about a month earlier than that of Borchers, where the reconstruction theorem is stated and proved in a completely algebraic fashion. These papers are not identical in content. You can also see it a little bit from the length. They are different, and but nevertheless they both have this essential idea of recasting the Wightman axioms and the reconstruction theorem in a framework which looks in fact extremely elegant, and is what is also used to this very day when you present the reconstruction theorem. Then the last of these seminal papers is here a review of the knowledge up to the year 71 by Borchers. This is this was a conference in Haifa called Statistical Mechanics and Field Theory. And here this paper also has some of the constructions which I will mention in the sequel. So this is really the only, to this day, I mean, this is probably the longest review of this subject that exists still, and maybe somebody should really expand on it because lots of things have, of course, also happened since. Anyway, so here is now the definition, and I am going to restrict myself to the usual case of a scalar Hermitian Bose field. Everything, of course, and even I'm going to assume that they have a temperate field. It could also be, of course, the test function space could be also the Schwartz space of test functions with compact support, like it was in fact in the Uhlmann paper. But for concreteness, I'm going to stick to this. And the Borchers-Uhlmann algebra is simply the tensor algebra completed in its appropriate topology, the tensor algebra formed over the space of test functions by which the quantum fields are smeared. And these are, the dimension is of course variable. To be interesting, it should be larger or equal to 2, but the physically most interesting case is of course 4. So here is the concrete definition. The notation S0 is simply the complex number. Sn is the n-fold tensor product of this completed, so it is simply the test function on R to the nd. And the elements are terminating sequences, so finite except, so to say, from here on, from some number on, which depends on the element. You have simply zeros. And the product is simply the tensor product. So the nth component of such an element of the product is a function now of n variables, and it's given by the usual tensor product of functions. So there is also an antilinear involution, which is obtained by taking a complex conjugation and inverting the order of the variables. Now, via GNS construction, as we talk about it now, there is a one-to-one correspondence between the cyclic star representations of this algebra by Hilbert space operators, denoted by phi f, and these will in general be unbounded operators. There is a one-to-one correspondence between these representations and positive linear functionals. And the positive linear functionals on the algebra are precisely those elements of the dual space. So they consist here of sequences of distributions. This is just a complex number. These are the distributions in the dual space of the test function space, which are positive on the squares in the algebra. And the correspondence, as in the usual in the GNS construction, is simply given that this expectation value here of the field operators, this is, so to say, is a polynomial in the field operators. Just by this compact notation, I can write it in this sleek form, because this has, of course, many components here, this function here. And this is the cyclic vector, and this is normalized if the length of the vector is 1, and that means that the 0th component has to be 1. And the here is just a notation. I will denote this positive linear functionals by S prime plus, and the normalized elements, that are those with omega 0 equal to 1, will be called states. Now, one of the first general mathematical results about the algebra is due to Lafner and Uhlmann, and was published in Communication Mathematical Physics in '68. And this result was that positivity put, so to say, no constraints on the representation, in the sense that the positive functionals, they separate points in the algebra. So the algebra has a faithful Hilbert space representation. Now, this result is maybe not so surprising, because after all there are no relations here. This is, so to say, a completely free algebra, but a priori you could expect that maybe positivity well puts additional restrictions, and as we will see, in fact, topologically this is the case, but algebraically that is not so. If you just consider the algebra, then you have this basic result here, this basic fact. Now, there was a stronger result proved somewhat later, and that was the result that positive functionals can in a certain way be arbitrarily singular in the sense of distributions, namely that if you give a continuous seminorm on the algebra, which means that the seminorms on the algebra can be simply the seminorms on the test function spaces, and they are simply then added up to get a seminorm on the algebra here. If you take such an arbitrary seminorm, you can always dominate it by a positive functional. And the components of this seminorm here, their degree, so to say, the number of derivatives and the powers of 1 plus x squared involved, they can grow with the number of components. So this can be a very big seminorm. And nevertheless, you can always find a positive functional which dominates it. So this implies, of course, in particular, that points are separated. Now, the corollary of this is a characterization of those linear functionals. This is a purely mathematical result, of course, still, but of the linear functionals which belong to the linear span of the states. Namely, they are characterized by a certain continuity property that the bilinear form here defined by the functional has to be jointly continuous. This is not trivial because the product on the algebra is only separately continuous. And in fact, just a little example which shows a little bit about the subtleties which are involved when you combine positivity and the topology here of the test function space. Here is an example of a linear functional on the algebra which cannot be written as a linear combination of states. Namely, well, you simply take the delta function and some derivatives with respect to some variables to the order n, and take the tensor product of this, and you let this order here grow with the number of variables. You can simply see that this will never be representable by a linear combination of positive functionals, because positive functionals, they satisfy the Cauchy-Schwarz inequality, and that will simply violate the structure here. Now, so far, of course, there is very little physics here. The only physics, if you like, is the probability interpretation of quantum mechanics, which is the positivity condition as it stands here. But the real meat on the bones comes when you put in conditions. And these are, of course, the physical conditions of causality, which is encoded in local commutativity, stability, spectrum condition, and the relativistic invariance. And the beauty of this algebraic approach is that you can formulate these conditions in terms of natural algebraic structures, namely the locality in terms of the locality ideal, which is the two-sided ideal generated by the commutators if the supports of the test functions are space-like separated. Likewise, the spectrum ideal is the ideal generated by the elements. You take an arbitrary element of the algebra, and then you translate it. This alpha A is the translation in space, so it acts on the test functions like this. And then you integrate it here over a function which has a Fourier transform in the complement of the forward light cone. And you take the left ideal generated by these elements here. There is a more explicit description of it, but this is a particularly nice algebraic way of describing it. You can also use this way also in the C star context, so I prefer to write it like this. So these are the two ideals, the locality ideal, spectrum ideal, and then you have also the translations I had written here. You have more generally Poincare transformations, also Lorentz transformation. They operate on the test functions, and that is the way they do it. Now, once you have defined these concepts, you can state precisely what is a Wightman functional. A Wightman functional is, by definition, a normalized linear functional, or a state on the Borchers-Uhlmann algebra, which satisfies the following conditions, which are the Wightman conditions. First of all, it's positive. It vanishes on the locality ideal, it vanishes on the spectrum ideal, and it's invariant under Poincare transformations. So these are conditions now formulated on a completely concrete algebra with a concretely defined ideals and concretely defined automorphisms. So this looks all extremely elegant and seems to be a starting point of a very long friendship between physicists and these Wightman axioms. Well, of course, as you will suspect and know. Things are of course not at all so simple as they may look at first sight, and I will have something more to say about that. But now what I want to discuss first are some elementary operations that you can do with Wightman functionals. You will maybe, the connoisseurs among you will notice that I have left out the cluster property. That it has a, so to say, a special role that has to do with the uniqueness of the vacuum. That can be dealt with by integral decomposition theory, so I will leave that out. Although that is less trivial in this case as in the case of C-star algebras. But anyway, if we forget about the cluster property, there are certain elementary operations that you can do here in the set of Wightman functionals. So these are, so to say, operations which will make new Wightman functionals starting from old ones. One is you can simply take convex combinations. Of course, you will, in this way, you will violate the uniqueness of the vacuum, but nevertheless, you will satisfy all the linear conditions and positivity. Then there are two products, two nonlinear operations which you can do. One is has been called by Borchers the P product, and it's simply the pointwise product of the Wightman functions. Well, you might object and say, well, this is not defined because the Wightman functions are distributions. What does it mean? Well, because of the spectrum condition, this is perfectly well defined. The easiest way to see it is maybe to say that you can, by the spectrum condition, you can extend these to analytic functions, and there the product makes perfect sense, of course. Or you can also say in Fourier spaces it's just convolution, and because the functions have support properties in cones, this is well defined. So the only non-trivial aspect here is that this is a positive linear functional again. But this is, so to say, corresponds to the Kronecker product of matrices. And then there is another product which is related also to truncation, and this is you take two functionals, then you sum here over all partitions of these of the indices 1 to n into two groups here, and then you take the appropriate mu point functions and nu point functions, and you take the sum of all this. And this is another operation which also leads to a new Wightman functional if you start with old ones. Now, here is also a remark that this product can in fact be defined not only for positive functionals. You don't need positivity for it. It's just that if you take two positive functional, then the result will be again a positive functional. Also, you can define infinite power series with respect to this product. If you have a power series with an infinite radius of convergence, if you have it as a finite radius of convergence, there will be a condition on the T0 component. But in particular, you can define the exponential function with respect to this product of an arbitrary linear functional. And this operation will then also satisfy the linear conditions if you perform this. Now, conversely, you can invert this operation by taking the logarithm, and this is just the truncation. So this is a very nice algebraic way of defining truncation. There is a sufficient but no means necessary condition for this exponential function with respect to this product to be positive, is that t is conditionally positive, namely that t of a square is positive for all f's with a 0 component equal to 0. Now, these notations are, in fact, have analogies in the commutative settings. So this can be understood as non-commutative extensions of some notions from probability theory. And you can, a natural question, for instance, is the converse question, whether if you have a given functional, whether you can decompose it into non-decomposable fields, which you could call prime fields. And this question was studied, in fact, by Hegerfeld in 2 papers. Well, this is, so to say, in the Wightman setting, and this later paper 10 years later is a paper in a more general setting for noncommutative probability theory. Now, I mentioned these things which may be known to many of you, but my guess is that this is not known to everybody. In fact, one justification for me to give this talk was that I also hope to convey some messages to young people about some basic facts which are not so easily found in textbooks, are widely scattered, and I thought it might probably maybe be useful for you to have them collected here so you know about them. Now, of course, this is the big scandal still of quantum field theory. The known examples of Wightman fields in dimension 4 or larger has not increased over the past 50 years, almost. Well, because these notions of the P and the S products were not so clearly spelled out for a while, so you can say they are a new ingredient. But what are they? You have the generalized free fields. You have the Wick polynomials and certain generalized Wick polynomials in such fields. And you have fields which are obtained from these two by convex combinations and by S and P products. And now I want to warn you that although this looks a little meager, the structure of such combinations can be extremely complicated. And if somebody presents you with an example and tells you, here I have a new Wightman field, it may be extremely tricky and far from obvious to entangle, so to say, the structure and, for instance, see that it really belongs to this set. And as a little anecdote in that context, I think it was about 10 years ago, Henning Rehren may remember it better. There was a paper by a mathematician who claimed to have constructed new examples of Wightman fields. And this was it was entirely motivated by the desire of a mathematician to construct a Wightman functional which satisfies all the conditions. He was not at all concerned about physical justification or anything. Well, anyway, so here was this list of Wightman functions with an extremely complicated construction, and the first thing was, of course, to check whether it satisfies all the conditions, and that turned out to be the case, if I remember correctly. But what was it? And I must say I really admired Henning Rehren extremely for his stamina, because he was able to look through the mist and see that, well, it is really a generalized Wick polynomial of generalized free fields. And this was, I think, a great achievement. Okay. Anyway, so why is the construction of Wightman functionals so difficult? Well, it's only one aspect of this question is to make a comparison with the C-star situation. Of course, it's only one aspect. You can say lots and lots and more about it. But if you, nevertheless, I think it's instructive to bear the following in mind, that if you have given a C-star algebra, then you can rely on the fact that the cone of positive elements in the algebra has interior points, to use extension theorems to construct states. So you only have to construct them on some subspace, and then you can always extend them. So this is one way. To obtain translationally invariant states, you can use the fact that the translation group is what is called an amenable group that has an invariant mean, so you can simply do that. You always have bounded functions, and you can do that. And if you want to construct states which vanish on a left ideal, then you can apply the fact that every left ideal is generated by a projector in the enveloping von Neumann algebra, and you can use that. Of course, it can happen that you will always get something trivial in this way, and this is the example of Sergio de Doppler here, for instance, where he gave an example of a C-star algebra, local C-star algebra, which did not have any representation satisfying the spectrum condition. But anyway, you have these basic tools, and none of these tools is a priori available for the Borchers-Uhlmann algebra. Nevertheless, this algebraic formulation of Wightman theory, it certainly raises natural questions about the compatibility between positivity and one or more of the linear Wightman conditions. And such questions were discussed and considered by several people. I should also mention here, which I have not done so far, that the Borchers-Uhlmann algebra was also studied particularly intensely in Leipzig, maybe more from a mathematical point of view, but there were lots of results obtained about the mathematical structure of this kind of algebras and related questions by Lassner and his students, among them Gerald Hoffmann, who is here today, and also, of course, by, well, I already mentioned this first result by Lassner and Uhlmann. Anyway, so I'm only going to quote 2 or 3 results which I managed to obtain when I was really seriously engaged in this enterprise in the 80s and 90s. And I have chosen here only a few such results which can be formulated in a rather slick way. There are much more results, but these I think they at least look particularly nice, so that's the reason I have chosen them as a sample. One is here about the compatibility between spectrum condition, translational invariance, and positivity. And this is I have chosen here a formulation, so it looks exactly like the theorem I quoted before, namely for every continuous seminorm there is a positive functional which dominates it. But here is the additional thing, is that this seminorm now vanishes on the spectrum ideal and is translationally invariant. And the functional here is not just a positive linear functional, but it also vanishes on the spectrum ideal and is translationally invariant. So it satisfies these parts of the Wightman axioms. And you have lots and lots of functionals which satisfy this. So this is now the construction. So this is really done in a constructive way, and I'm just quoting here the results and not saying anything about the method, so you may wonder how it is done. And well, I can say quite generally now, maybe to save time, I will just say that most of these results are obtained by using the fact that the test function space is a nuclear space, and in fact a space of a special kind, where you can define the topology by Hilbert seminorms, which are given by powers of some fixed operator. That's one thing. Another thing is this S product, which I had mentioned before, and the fact that maybe I go back to this, namely that if I have a conditionally positive functional, then the exponential of it is positive. And this is also something that is used repeatedly in these constructions, just to give you an idea of what is involved there. A corollary of this is that you can characterize now the linear functionals which belong to the linear spans of translationally invariant states which annihilate the spectrum ideal. And here is a condition which is should be maybe compared to the previous one, which was just here, namely that it was jointly continuous, this product. Here you have, of course, more, and the condition is here. Namely, not only has this to be jointly continuous, but also if you translate here and you integrate, then you have to have this estimate here. It means in particular that as a distribution, this expression here has to be the Fourier transform of a measure. So this is something which follows from translational invariance and positivity. Now here is a result about the locality ideal and translational invariance. This result is obtained in a different way, by a completely different construction, namely by mapping the Borchers-Uhlmann algebra into what we called partially commutative tensor algebras over finite dimensional spaces, and studying such algebras. That's a kind of a discretization procedure. And there you could also prove a result a little bit similar to that, but I prefer to present here a result which is a little surprising, in fact. And it's about bounded representations and locality. Namely, it can be formulated in this simple way. The algebra, the quotient algebra of the Borchers-Uhlmann algebra with respect to the locality ideal. So this is, so to say, the free algebra where you have no relations except those imposed by locality. This algebra has a faithful translationally covariant Hilbert space representation by bounded operators. And this result is rather surprising and leads to the question whether the field operators of Bose field can be bounded operators in a Wightman theory. Namely, whether there exist bounded representations of this quotient algebra here satisfying the spectrum condition. The spectrum condition is, of course, here the really tricky thing. And such fields would certainly be new examples. I'm not saying that they would be really very important for physics, but if you really want to understand what is behind these axioms and whether we are stuck forever with these examples that we know, I think this would be a very interesting thing to understand. Now, in 2 dimension, there is a very simple example, and it was shown to me by Detlef. I think it was about 1994, maybe it was in, so what, no, this was,
the beamer went off?
Beamer went off, okay. Der Beamer ist überhitzt, oder? Abschalten und warten, oder wie? Ja?
Er hat sich selber abgeschaltet. Ich kann ihn gar nicht wieder einschalten.
Ach so, okay. So let me then just try to continue. I was saying something about bounded Bose fields. I was saying that they would certainly be new examples, and therefore mathematically, I think, at least quite interesting. The first example, as I said, was presented by Detlef, and that was simply by taking the tensor product of 2 Fermi fields on light rays in 2 dimensions. So it's coming back.
Just wait.
Okay, we can just wait. Now the wow. Okay. So the general structure of analysis of such fields, well, there was in fact Henning Reren presented lots of examples using more complicated ingredients in 2 dimensions, and the general structure of such fields which satisfy conformal covariance and the Huygens principle was undertaken by Klaus Baumann, as I said, and also by Grott and Reren. And in that case, namely if you have conformal covariance and the Huygens principle, their conclusion was that there is no scattering, even if the Wightman functions can look quite complicated. In that case, whether that is general feature in 2 dimensions or if it is also the case in 4 dimensions, that is still an unsettled question. Now I want to go here briefly into something which was, so to say, a byproduct of this endeavors of understanding the states on the Borchers algebra. The Borchers-Uhlmann algebra, and that was done by extending the algebra by including something which could be called abstract resolvents. And the motivation for this was that we wanted to understand the relation between the in general unbounded field operators and local nets of von Neumann algebras. This is, of course, a classical problem in the comparison between Wightman theory and the Haag-Kastler or Haag-Kastler-Arati framework. And so this extension is obtained by, well, for notational reasons, I will now denote this quotient algebra here simply by P. And you should think of this, so to say, as partially commutative polynomials in the test functions. And it can be regarded as a free star algebra with generators, the real test functions, and the relations are simply commutativity if the test functions have space-like separated purport. The unit is denoted by 1, and now this algebra is extended to a new algebra by adding simply new generators, which I denote by R plus and R minus, which is supposed to be the adjoint of R plus, and the relations which stand here, which simply tell you that this R plus and R minus are, so to say, on the abstract level, the inverses of these F plus or minus I. So these are the abstract resolvents. And the relation is, of course, that these resolvents should also commute if this is space-like. Now, this is what I just said here. And a remark is that such abstract resolvents have recently been applied by Buchholz and Grundling, however, in a different way, with more relations, because they are involved in, they are interested in the CCRs. And so they define in this way a novel C-star algebra. So this is just to remark that, that such extensions are also nowadays quite interesting for other purposes. Now, one defines now the set of bounded elements in this abstract algebra here as the elements of this form here, some power of the test function and some higher power, or at least as a high negative power. So this is, so to say, formally bounded, and this is what we call bounded elements. And then we define a positive cone in the algebra in this way. This looks a bit complicated, but this is, so to say, nevertheless manifestly positive in a way. If these were just functions, you would immediately see that this is just a square, so this would be positive. And now is a result by Borchers and myself about self-adjoint extensions, leading in possibly out of the Hilbert space. And it's the following: if you have a state on this partially commutative algebra here and corresponding field operators, then the following are equivalent. That the state is positive not only on the squares here in the in this polynomial algebra, but also on these extended squares, namely on the positive part of this extended algebra, including these resolvents. This is equivalent to the operators having self-adjoint extensions, possibly in a larger Hilbert space, such that these extensions, they commute strongly in the sense that the bounded functions of these self-adjoint operators, they commute if the supports are space-like separated. And now this general result can be combined with some previous ideas of powers on the one hand, on the purely mathematical side, and by Driesler, Summers, and Wightman, 1986, to derive a criterion for the existence of local nets of von Neumann algebras associated with a given Wightman field. And there are two more concepts that are needed. One is the concept of the weak commutant. If you have a set of closable but in general unbounded operators, then their weak commutant is defined as the set of bounded operators that commute, so to say, in the sense of matrix elements. So you never have to worry about domains of definitions of the product. So to say, you never apply C to some element in the domain, but you do everything in the terms of matrix elements in this way, so you never get into this problem. This is the weak commutant. And another concept is the concept of a centrally positive state on an abstract star algebra. You consider the cone of squares in the algebra, namely the cone generated by the squares. And then you say that the state is centrally positive with respect to an element in the algebra if it is positive not only on all squares but also on all the elements of this form here, where an in the algebra are such that this is a square, or rather a sum of squares for all real numbers R. That this is not the same as being simply positive is seen by the standard examples of so-called Hilbert polynomials, which are polynomials in more than one variables, which are positive but cannot be written as sums of squares. So this is a stronger notion than simple positivity. Anyway, so here is our result about the local nets of von Neumann algebras corresponding to a given Wightman field. So state and denote by PO the sub-algebra of this abstract quotient of the Borchers-Uhlmann algebra here, generated by the test functions with support in O. This is a very natural notation. And a different P, namely calligraphic P, the corresponding star algebra of the operators in the GNS representation. And now if you know that the weak commutants are not only weakly closed, which they always are, but and this is of course always a weakly closed linear space. But if you know that the product of two elements here is also in this set here, this is something which is not automatic. If you know that, then the following statements are equivalent, namely that this net, very concretely defined net of von Neumann algebras, is a local net. That is, the algebras corresponding to space-like separate regions commute. And the equivalent condition is that for every open set and every real test function with support in this open set, the state is centrally positive in the sense defined before on the sub-algebra generated by F and the test functions with support in the causal complement. And now this condition that this here, that this weak commutant is an algebra may look terrible. I mean, how would you check that? But fortunately, it is possible to check that by fairly weak energy bounds. Namely, if you know that the field operator its closure multiplied by this exponential function here of the Hamiltonian, essentially e to the minus Hamiltonian to the power alpha. If this power is less than 1, then you know that these weak commutants are in fact von Neumann algebras. And you say that this satisfies a generalized H-bound. So this is a very useful criterion. But nevertheless, this you can, of course, check in a concrete model. More difficult, of course, is to check this central positivity, because that is a rather tricky condition. But one good thing about that is that such positivity conditions are stable under limits. So if you construct your state as a limit of states which satisfies this condition, and that may be easier to prove for the approximating functions, then you know that it is satisfied. So this condition is maybe also even useful in practice. Now I have fairly little time left, and there are two topics I wanted at least to mention briefly. Well, the title of the talk is, after all, the Borchers-Uhlmann algebra and its descendants. I have mentioned one of its descendants, namely this extended algebra. There is another descendants or a family of descendants I would have liked to discuss, namely the use of the Borchers-Uhlmann algebra or the Borchers-Uhlmann type algebras in the quantum field theory on on curved spacetimes. But as I said, this was not possible here. Also, another topic which would have been maybe worth discussing is the Euclidean context, the Osterwalder-Schrader positivity, the representability by Schwinger functions, by measures, etc. That is another topic on which we worked in the 70s and in the 80s. But now I want to mention just, or rather make propaganda for the lecture of Gandalf by just mentioning that deformations of the Borchers-Uhlmann algebra have been used quite recently to discuss deformations of local nets, deformations which deform the nets in such a way that you may not fulfill the full locality, but you still fulfill wedge locality. And one way of there are, so to say, the main the first papers were by Grosse and Lechner, and it was this was essentially for free fields, the first papers. But then there is a more general paper which also works for interacting Wightman fields, and this was also taken up by Detlef and Stephen Summers. And Morpha Morales is also working on this in Vienna. Now, the formulation I want just to mention here is based on the deformation of the Borchers-Uhlmann algebra. And I will probably not go through it here in all detail, because this is something that Gandalf will talk about. But so this is, so to say, just a preparation for his talk. And it's based on the Moyal tensor product of two functions. Namely, if you have given a so these are functions now on 4 space, or rather on the nth tensorial power of 4 space. And if you have two such functions and you have an antisymmetric 4×4 matrix, then the Moyal product is defined in this way. Namely, you take here these two functions here, multiply them pointwise, then you translate by a psi and here by a q, and then you multiply by this phase factor and you integrate here. This is the deformed product. And this extends to a bilinear separately continuous associative product. And you can also do it here for different thetas, of course. And this is associative for if you have a fixed theta, but in general you do not have it if you have here different thetas. Now, if you have a Wightman state, you can define a deformed state in this way. And this means, in the terms, you can write it explicitly in terms of the Fourier transforms, that you simply multiply here by a phase factor. And now this twisting, so to say, of the Wightman functions is something which is only non-trivial for the higher point functions. For the 2-point function, 1-point function, it's not defined. For the 2-point function, it's just the same. So you see it for the 3-point function and higher. Now, an important remark is that these different deformations, namely corresponding to the different antisymmetric thetas, they can be defined on a common Hilbert space, namely the Hilbert space of the undeformed field, defined from the original field. And now there is another, there is a correspondence between these antisymmetric matrices and wedges. And a key result of Grosse and Lechner is that the deformed fields, even if they are not local, they are still wedge local. And this is what is stated here. And here, and this result is also in the Borchers, in the Buchholz-Summers formulation. This is a result which they prove in the context of C-star algebras. Here it is proved in the context of this Borchers-Uhlmann algebra, deformed. Now the last problem I want to mention here very briefly is a question which, as I already said or mentioned, was posed at the very beginning of these investigations in the 70s by Borchers. And it's the following. Well, as you know, it's the most general structure of a 2-point function in Wightman theory is simply the Hellen-Lehmann representation. And so if you have any such function, then you can always extend it to a Wightman functional, namely that of a generalized free field with the given 2-point function. Now also, and this can be a very sophisticated result, variants of which were proved, for instance, by Klaus Baumann. If the Lehmann weight decreases sufficiently fast with the mass, then the extension is even unique. The original version of this was of course, the Jost-Rower theorem, which tells you that if the 2-point function satisfies the Klein-Gordon equation, then you necessarily have a free field. Now, anyway, knowing this, a very natural question appears to be the following. If you have given 2-point functions, let's say W2 up to some W2m with m larger or equal to 2, in particular, if you have given omega 2 and omega 4, which additional conditions are necessary if you know, well, let's suppose that you know that they satisfy the Wightman conditions when you restrict them to the test functions where they make sense, which additional conditions are necessary in order that this finite sequence can be extended to a Wightman functional on the whole of the Borchers-Uhlmann algebra. Now this is a formidably difficult problem. And in fact, I was rather soon convinced that it's completely hopeless. But some results which I have recently learned about might indicate that it's worth looking at it again. And so let me mention what I have in mind here. Namely, I want to compare it with a different but closely related, or rather somewhat related, how closely you can maybe argue about it. Formally, at least, it looks close. Namely, the famous representation problem for reduced density matrices in non-relativistic many-body quantum mechanics. to write it in a form so that the analogy with this quantum field theoretical problem is clear, then I have chosen here to write the Hamiltonian of a particle system in a second quantized form. So now you have to think that you have a system of particles, non-relativistic particles, and they are sitting in an external potential V, and they have a two-point interaction, let's say little v. And then the Hamiltonian can be written in, with creation and annihilation operators in the following form. Here is the kinetic energy. Here is the interaction with the external potential. And here is the interaction between the particles. And here you have these creation and annihilation operators. So this is the way of writing the Hamiltonian. Now, if I now have some wave function and particle wave function, I denote in this way the expectation value, then you see, of course, that the expectation value of the Hamiltonian is completely determined by the so-called reduced 1 and 2 particle density matrices. Namely, these are simply the expectation values of a product of 2 creation and annihilation operators and the products of 4 creation and annihilation operators. So these are, so to say, the 2-point function and the 4-point function. And whereas the original wave function has, of course, extremely many variables. In fact, since you can always obtain the 1 particle density matrix by simply integrating out here the intermediate variable here in the 2 particle, it's really only row 2 that is needed. That determines everything. And this observation, and it was made apparently very early. In fact, I found somewhere that Coleman, it's not Sidney Coleman, of course, but Coleman in 1951, he observed that, well, this is apparently a vast simplification of the question of the ground state energy of many-body systems. So all you have to do is to take the infimum over all possible row 2s instead of taking the infimum over all wave functions. Well, of course, there is a big snag to this. And the snag is a representation problem. Namely, it's not known which functions on R4D are possibly reduced two-body density matrices. Some necessary conditions are, however, known, and conditions which I did not know about until recently, in particular for fermions. And taking the infimum over all rows which satisfy such conditions, that leads in any case to a lower bound. And interestingly enough, such bound can even in some cases be quite good numerically. If you just take the most naive necessary conditions, you will get very lousy lower bounds. But there are, in fact, lower bounds conditions which will allow you to do that. Now here, as I'm just mentioning it, I mean, there is analogy with the extension problem for the Wightman function. However, there is also a big difference. Namely, this is always for the CCR or CAR algebras, and that makes things, in a way, simpler. But anyway, a necessary condition is in both cases that these functions can be complemented to obtain a positive linear functional on the algebra, in this case on CCR or CR. And this is now my last or second last transparency. In the Wightman case, very little is known about this extension problem, but there is a very simple necessary condition which simply comes from the Cauchy-Schwarz inequality. Namely that the 4-point function, you must be able to estimate it by the 2-point function and some continuous seminorm here. And you can, of course, then iterate it, because this really comes from a positive definite 6-point function, so you can repeat it. And that will lead to further, but of course more complicated questions. Now, this is then essentially the last thing I wanted to say. It's just a warning that if you just ignore the linear conditions and just ask if when you can extend a given 2-point and a 4-point function to a positive functional, there are examples that show that you will always need infinitely many conditions. You will never be able to do with finitely many. Namely, it's possible to construct an example of the following kind. You can construct a 2-point and a 4-point function such that you can, for a given n, you can extend it to functions here, f, which have at most n components. But it, so to say, carries the seed of death in it, in the sense that you cannot go one step further. So this is what I said, you will need infinitely many. But even if a complete solution to the extension problem is probably not feasible, the search for new necessary conditions might still merit further effort. Now, let me just then allow me to say a few words in conclusion. Well, I wanted to give you a review of some of the facts about the Borchers-Uhlmann algebra, which are known to me. This formalism has really proved its validity in many contexts, including quantum field theory on curved space-time, deformations, comparison with the von Neumann setting. And there are still interesting questions. I just mentioned two. One was the bounded Bose fields, another is this extension problem here. It's not that I'm not working on them. The reason for that is not that I don't find them interesting. It's just that, well, life is only finite, and there are other things that I have thought that I simply had to do, and things have simply turned out so that I have not been able to devote my time to this, but I would certainly be very happy if somebody would look into this and maybe have some fresh ideas how to proceed. Okay, thank you very much. Yes.
And there was a very interesting paper where you addressed the question which were sufficient conditions for these Schwinger functions to be moments of a complex measure in
exactly.
prime.
Yes.
And these conditions look very similar to ones you need to have an operator crowded expansion.
Exactly.
Can you say a few words about that?
Well, I mean, that was in fact on my original agenda. I wanted to have a few transparencies about that, but I don't know if maybe I should talk to you about this in private rather than taking up the coffee break for that. But thank you very much for mentioning this, because this is really something which, yeah, I think we really worked on very hard, and we're able to prove a result that looked surprisingly sleek, at least to us, and it was not quite so simple. Okay.
One more question.
Yeah.
You had a result there stating, giving a criterion when a field operator had a self-adjoint.
Yes. Yes. Yeah.
As that, well, I said it hasn't, but could you see that could be applied to let's say Wig products of the free field?
Yes. In fact, that could probably, because you could by this approximation method which I mentioned. Yes. I think that's well, because the Wick, as you know, of course, the Wick polynomials are in general not self-adjoint. But and they may even, in there are examples well, that's in one dimension, one space-time dimension. So it's, so to say, a quantum mechanical example where you even have non-symmetric defect indices. So they don't even have self-adjoint extensions in the same Hilbert space. But nevertheless, you could still have locality in the sense that bounded functions, if you take the polar decomposition, then you would get it. And that could, this criterion could in principle be applied by simply approximating it by a good, less singular object, where you would have this this positivity condition and take the limit.
Thank you again, speaker.
Okay.